a few other types of energy resources that exist. There are things called oil shales, and while they are called shales, they don't actually have to be shale. Many of them are, which is why they have that name, but some aren't. And this is going to be a sedimentary rock that contains something called kerogen. And kerogen is the remains of plants, algae, and bacteria. Typically, these oil shales were formed in ancient lakes. This is what an oil shale looks like. The U.S. has about 2/3 of the world's known supply of oil shales, so definitely have plenty of these. The reason why it's not used as much as, say, it could be is because processing it is difficult. Processing an oil shale to get the oil out requires a lot of water, and you get quite a bit of waste from that. The volume of waste increases is like 20 to 30% in many cases, and so you are going to you have to figure out how to dispose of that and take care of that. Now, why the water thing was important is, let's take a look at where a lot of the oil shales are in the United States. This is Wyoming, this is Colorado, this is Utah. In blue are the oil shale potentials. This is where most of the oil shales are. And I don't know if you guys have ever traveled to this part of the world, but it is, there's not a whole lot of water in that area. And so that's why this is a problem. The oil shales are there, the water needed for processing is not. Now, tar sands are another thing where we do get a lot of oil from, and in fact, a lot of the Canadian oil that gets shipped down here to some of the refineries comes from these tar sands. Tar sands are, again, a sedimentary rock that contains bitumen, which is this kind of really thick, gooey, sort of solid hydrocarbon. And this is what some of these tar sands look like. And tar sands can be extracted in two ways. They are sometimes extracted using strip mining, like the coal, right, where we take away the overburden, we scrape away the tar sands and then reclaim the area. But some of the tar sands are extracted in situ, which means we get the hydrocarbons out while leaving the rocks in place. And that's what we're looking at here. We might have some of these tar sands close to Earth's surface over here, so we do the strip mining, but they might be deeper underground over here, so that's where we do the in situ. And the way they do this is they'll have this steam injection, which heats things up. And when we heat things up, that changes the viscosity of these semi-solid hydrocarbons, makes them flow better. And when they flow better, then we can actually pump them out. We can actually extract them from the ground. Now, this does require a lot of water to extract and process, so this is similar to the oil shale difficulty, which is one of the concerns with this. Canada has some of the most extensive deposits of these sorts of things. And most of them are in Alberta. And so we can see that's where Alberta is located. And there's the different oil sand or tar sand areas that you can see. All right, another source of energy that's a very interesting source of energy is uranium. Uranium is a radioactive element, and so this radioactive decay, which is fission, of uranium produces heat. And this is what is going on in a nuclear reactor. In a nuclear reactor, we're having what's called a controlled chain reaction, a controlled fission reaction, where basically the fission of one atom causes the fission of another atom, which causes the fission of another atom. So there's kind of this constant release of heat energy in the nuclear reactor. And what happens then is the nuclear power plant works just like the natural gas or coal-fired power plant. The radioactive decay heats the water turns to steam, the steam turns a turbine, the turbine turns a generator, and we get electricity. Well, where do we get this uranium from? Uranium is an element that has to be mined out of the ground. This is, see this yellow stuff right there? That's a uranium-bearing mineral. So the uranium will then be extracted from that mineral, and it will be concentrated into fuel rods. And this is concentrated fuel-grade uranium pellets. So in our basic look at a nuclear reactor, we have our containment structure right here, where there's our reactor, and in the reactor we have fuel rods that are filled with those things that are giving off the radiation, and we have these control rods that control that fission reaction. And we get this water going into the reactor area, getting heated by that fission reaction, getting turned to steam, which turns the turbine, which turns the generator, which gives us electricity. And this is what a power plant looks like, a nuclear power plant. This is a cooling tower, and that's the emissions out of that nuclear power plant. And that is steam. It's just water vapor, and it is not radioactive. You could condense that and drink it and be perfectly happy and safe and healthy. So some people consider uranium and nuclear power to be a clean energy source. Now I put that in quotes because it's not entirely true. Some people say that because the only thing being emitted from the actual power plant should be water vapor. But like any energy resource, and I hope you're getting a clue here, there's no magic bullet solution to energy issues. Every energy resource has positives and negative aspects of it. So yeah, this is clean, but there are some issues to it. You have to be careful where the reactor is located. Think about what happened in 2011 when the earthquake and tsunami hit Japan. The nuclear reactor, it was Fukushima Daiichi, it survived the earthquake just fine. But what happened when the earthquake occurred, the earth shifted that area downwards and made it more prone to getting hit by the tsunami. And so you've got to be really careful where these things are located so you don't get some even like natural disaster like that to hit it and cause an issue. Everyone gets concerned about meltdowns like Chernobyl or Fukushima Daiichi. But I do want to point out that we've been using nuclear power since what, the late 1940s, and those are really the only two absolutely major full-on meltdowns. Granted, we had 3 Mile Island, which was a partial meltdown, not complete, not as bad as those. But when you think about how many nuclear power plants there are around the world and how few of these accidents have happened, they actually do have a pretty good safety record. The only problem is, when things go wrong, they really go wrong. Like, so again, there's the having the cost-benefit analysis, right? Weighing the risks versus the benefits is something that has to be done. Now, to me, what's a more concerning thing about nuclear power is the radioactive waste. What becomes of the radioactive waste? Because eventually, those fuel pellets still pack a radioactive punch that'll kill you, but they're not going to be able to make electricity anymore. That's the waste. We have to get rid of that somewhere. Right now, the U.S. does not have a national repository for reactor-grade nuclear waste. Basically, the power plant that makes it gets to keep it on site. They get to store it on site. We could make reactors more efficient. There are things called breeder reactors, which actually kind of reconcentrate the nuclear waste and reduce the amount of waste. They still produce waste, but they reduce the amount. They are very expensive to build, and the US does not have any of those. So again, nuclear power, there's pros to it, but there's also drawbacks to it. Let's look at solar energy. In solar energy, we can generate electricity based off two different ways. You might use photovoltaic cells. That's the technical term for solar panels. So photovoltaic cells, the way these work, inside that photovoltaic cell there's a semiconductor. And photons from the sun, photons of light, hit the solar panel, excite the electrons in the semiconductor, and this like flow of excited electrons makes electricity for us. And this is a solar array off in Colorado. And what is kind of neat about these solar panels are movable. And so as the sun crosses the sky from east to west over the day, these things actually rotate following the sun so they capture the maximum amount of energy. Now the other way we can generate electricity from solar energy is something called concentrating solar power. And this is where you have a concave mirror, so a mirror can curve like this, and it focuses sunlight, and thus its heat, on an oil-filled tube. And this oil gets heated to about 750 degrees Fahrenheit, gets run through some water, which then boils, right, turns to steam, and then guess what? The steam turns a turbine, which turns a generator, which makes electricity. This is one of these concentrating solar arrays. There's that tube filled with oil. There's our mirror that focuses all the sun's energy on that tube. Don't stick your hand there. It won't be pretty. So what are some of the advantages to solar energy? Well, it is clean and it's renewable. If the sun comes up, you can be making electricity. So that's really nice. And we don't get any kind of emissions. We don't get water vapor even. We don't get, at least not from photovoltaic cells. We don't get carbon dioxide or sulfur dioxide or any of that stuff. However, those photovoltaic cells contain things like gallium arsenide and cadmium telluride, which are not good, right? One has arsenic in it, one has cadmium, a heavy metal. So what that means is when your photovoltaic cells no longer work, you can't just dump them anywhere or those pollutants could get into the environment. So you have to be really careful how you dispose of them. They do require lots of land because you have to set up these arrays of solar panels or mirrors. Now, we could use land a little better. Like some places in California, their parking lots are actually covered. And the roof of the parking lot are photovoltaic cells. And so there you're kind of doubly using that land. You can park there, but you also are using it as a solar array. Of course, it's going to cost money to develop that, but it's not a bad way to use land like that. So these require lots of land, but you can be creative at how to utilize land best. A big problem is it's difficult to store energy. What we really could use are really good batteries. Battery technology's gotten better over the years, but it still could be improved even more. And then there's the other thing about solar energy. It is limited to certain areas. It's only really effective in parts of the world. This is a U.S. map looking at like days of sunlight or the amount of sunlight arriving in different places. You can see here, like the southwestern United States would be awesome for solar energy because they get a lot of sunlight. But you know, if you're living up in Seattle where it's raining almost all of the time and you don't really have all that many sunny days, well, you know what? It's not going to be as effective an energy source. Or then think about like where my family's from. It's up in northern Norway, the sun doesn't even rise for part of the year. And so that would kind of suck if we didn't have electricity for part of the year. So there are drawbacks, but I think solar energy is something that could be utilized more in certain places. Now, geothermal energy is another really neat one. This is where the Earth itself heats water into steam. So this is going to be used in places where you have volcanic areas where magma is close to Earth's surface, it's heating the groundwater, and we can then use that hot groundwater to generate electricity. This is the Wairākai geothermal power plant down in New Zealand. It's been operating since the 1950s. Geothermal energy has some advantages. It is clean. Again, we're not putting ash or sulfur dioxide or carbon dioxide or any of that stuff into the environment. It is renewable. As long as your magma's down there heating up water, you can be making electricity. And once you install the power plant, it's quite inexpensive to continue the operation. There are disadvantages to this as well. The plant is going to have a footprint to it, right? We're going to have all these pipes. What those pipes are doing is they're extracting some of this hot water in some areas and they're injecting water back into the aquifer to be reheated in others. You wouldn't want, like in Yellowstone National Park, all these pipes going all over, right? So you have to think about that footprint, where the plant is going to be located. And again, this is limited to certain useful areas. I said you have to be in these volcanic areas where we have this hot groundwater. In a place like here, this isn't going to work because we just don't have hot enough groundwater to be able to generate electricity from it. All right, hydropower. Hydropower is using dams. We're using the potential energy of water held behind a dam to turn turbines. So basically the water level in front of the dam is here, the water level behind it is here. And in this dam, there are intake areas where the water way up here goes through the dam, through these turbines, and as it flows through those turbines, it spins them to generate electricity. That's what we're seeing here. Here's some of the turbines in a dam. This is a different one than the previous one. This is in Wisconsin. And so there's water flowing under there, spinning these turbines, spinning the generators and making electricity. And again, this doesn't have any pollution and it's relatively inexpensive. But installing dams in places has many far-reaching effects that should be considered. You have limited locations where you can build an effective and safe dam. Dams themselves are prone to failure, which can end up killing many people if you have this massive flood when a dam breaks. Dams are known to damage ecosystems because you're changing from having a stream ecosystem to a lake ecosystem. And there's organisms that don't like that change. There's the destruction of historic sites. When you build a dam, you're flooding an area. You could flood many different places, including archaeological sites and also even just towns. There's a dam down in southern New Mexico, Elephant Butte Reservoir. You can go scuba diving in an old town that's underwater now because it basically got flooded when they installed the dam. We talked about silting of dams when we talked about flood control dams, the buildup of the sediment behind them. And they can completely alter a river system because they can start affecting where erosion and where deposition happens on the river system. So they don't just alter the life on the river, but also physically alter the way the river behaves. So again, there's positives and negatives to hydropower. So the last one I'm going to talk about is wind power. Wind power has been used for a long time. If you go to parts of Europe, you'll see windmills, and this particular windmill was built in the 1400s, and it was built as a mill to grind grain. You would take your wheat or your barley or whatever over there, and this would grind it down into flour. Nowadays, we tend not to use it to grind our grain. We use it to generate electricity. You have these wind turbines, and the wind spins it, and there we go, we're spinning it in order to generate electricity, right? So, advantages: it's clean, it's renewable. As long as the wind is blowing across the Texas plains, you're going to be making electricity, right? And we're not producing any kind of nastiness from it. However, there are drawbacks again. There's aesthetics. Aesthetics is like how things look. Again, if you have this beautiful mountainous area that's just absolutely breathtaking, you're probably not going to want to like stick wind turbines all over it, right? Because we do still want to have some beauty in the world. There's limited locations. You definitely need places where you have strong enough and steady enough winds. You need a lot of turbines to generate electricity. I did a calculation some time ago that like 10 years ago, for the population of just the city of Houston, you'd need something like 4,000 wind turbines to give them enough electricity. I'm pretty sure that calculation has changed. You probably need more now. But that's a whole lot of wind turbines, and that's just one city in the United States. So you need a lot of them to generate electricity. And then after a while, they don't work anymore, and you have to dispose of these massive things. And that's a serious question. Where are we going to dispose of these massive wind turbines when they have outlived their useful lifespan? Now, there are a number of other alternative energy resources that I didn't cover. There's things like tidal power that's used in some areas. People have been looking at hydrogen fuel cells. And there's lots and lots of other alternative energy sources, because this really is something that is being researched today, looking at new and better and cleaner and more efficient ways of making energy. But I hope what you're going to take away from this lecture is the fact that no one energy source is the perfect energy source. All of them have good aspects and bad aspects, and can be better for certain places than others. And that brings me to the last picture. This is my random picture of the day. That was my dog Milu. Milu came from Africa, from Djibouti, and he was part Basenji, which means he didn't like to bark, he liked to yodel. And you should YouTube Basenji yodel to know what I used to have to listen to at like 3 in the morning. So anyway, that's energy resources, and I'm signing out.